comfortable, or you prefer to?
No, here's fine. Like, hey computer, can you hear me? Hey computer. Final presentation. Okay, Google Slides. I'm going into Google Slides. Hola.
Sí. Sí. Vaya, la transmisión. Borré el anterior. Sorry. ¿Me tenía ahí? Parece que sí, así que lo volví a activar. Pero ahora está en vivo. Ya, y ahora, ¿cómo lo hago para acercar, configurar video?
Okay. Incognito. Yeah. Well, I think it's so good. Go to Google Slides.
Tutorial mix.
Okay. Oh, there you are. Okay.
So, how do you want to be introduced?
Abrí esta versión.
I'll go through things very fast again.
I can introduce you as like the information that you sent us afterwards. Your name is Sheng Taoyang.
Yeah, Cheng Da Yang.
Mi señora nació en Chuquemata y mi hermana también.
Chang'an University. Chang'an.
A rajo abierto porque ahora todo es subterráneo. Entonces se hizo la ceremonia de la última tronadura. A la última, todos los días.
We don't really mind. Yeah. Oh, I'm a mic. Look at that. Oh. Hola.
Tu cabeza la que estoy viendo. Un poquito más cerca de Alejandro.
Yeah, don't be afraid.
Exactly, you're blocking the To be famous.
Oh.
All over the world.
This room has very nice lighting.
Yeah. Probably it's like hell in summer, though.
Oh yeah.
also nicknamed Andy, who is going to is coming from the Shanghai University, from the Faculty of Medicine. He's a third year student. He's third year student from the career, and he was spending like a internship here at our university. And he's going to work in things like instrumentation of cell images that probably he will mention it later, but in this case he will present us a review of a paper which is related to cell image processing in using some machine learning.
Great. Okay. Thanks for everyone for coming to listen to this review of the applications of machine learning in cell images. I am a medicine student, and I'm very glad I have this opportunity to come to this very integrated lab with multiple disciplines and to have a look at how machine learning is applied in the field of medicine. In this case, the medical images. So we choose this paper called Machine Learning Applications in Cell Image Analysis by Ken. And it's a very recent paper published in 2017 summarizing what is machine learning and what type of machine learning there are and who has developed algorithms to apply machine learning in the field of their interest. And in here it's cell images. So I'll jump into the point to share my feeling of why we need machine learning. So imagine now this is a photo of the lymphocytes, and then one day if we want to reconstruct the B lymphocytes image to a 3D one, it is very hard to sometimes based on the image, human beings it's very hard to know where are the borders and what is the nucleus like. So why do we need machine? Because the differences between machine and human is that they can carry out repeated tasks, and they can do complicated calculations that that a human would take a lot of time to do. So if you imagine that if you want to reconstruct a 3D nucleus manually, it would take a lot of time. First, you need maybe a marker to mark where you think is the border, and then you have a lot of slides, 2D slides, and then you need to find a method to construct them back into a 3D. But what if a machine can know, based on how you train them, to know where the borders are? So I only need to mark one slide, for example, because I know for each slide of the image, the border looks roughly the same, and the signal is similar. So what if I can mark it, and then I can train another person to do the job for me for 28 more slides, and then we reconstruct it together. That is the idea why we need machine learning in the first place. And then of course we do machine learning on the computer. And I put this picture because what are the materials you need to train the machine? For example, if you are having this machine, the input is cloth and the output is clothes. So in the same similarity with the machine, you need to put some inputs, and then you will have some outputs. And how do you make a machine learn? You have to use an algorithm. An algorithm that may be complicated, but it can tell you a model that can use for prediction. So there are two types of machine learning. The first type of machine learning is called supervised learning. And the goal of supervised learning, one of the goals is to develop predictive model based on your input and output. So with supervised learning, you can have classification. You can tell that if this is a phone or not the phone. The machine is supposed to be able to tell you. That is classification. Or if you have a set of continuous data, you can run regression, meaning that you can find a function that fits the data, the original data, and can use for future prediction. And the second type of learning is unsupervised learning. The differences between supervised and unsupervised learning is that in unsupervised learning, there is only input model, but you don't have an output model to train the machine. And the purpose of unsupervised learning is to explore the data structure, to know some information in the data that is blind to the human eye. But after some numerical processes, you can see if there are clusterings. And I will talk about it later. But first, I will talk about supervised learning and what they are. This is the flow chart of supervised learning. So, so you have a bunch of data, and the idea is not to train all the data, because how do you know that the model that is outputted by the computer is useful? You need the same set of data for testing. So, so usually we separate the data set into a training set and a testing set. And with the training set, it would go into a box of algorithms, and it will tell you, it will fit the model. So the first result will be a model, and then with the testing data, it can know that if the output from the model is close to the real output. So there is a modification process in this learning to minimize the differences between the algorithm output and the real output in order to find the best model, to train the best model. And after the training process, once you have a model with a good accuracy, you can use for future prediction, which is here. And this is supervised learning because train model, they are based on manually labeled data. You are telling the computer what you want to train, what features there are. And secondly, I mean, it is used for predicting the rest of the samples, which is here in this part. So that is the basic idea of supervised learning. So now I want to jump into more methods of supervised learning. The first method is decision tree. And decision tree is simply a branch that looks like a tree, but there are some threshold values. For example, in this example, if you want to know a signal if it's a cell or a debris, there are some features you care about, such as segment area or elongation. But as a researcher, you don't know exactly what the value of A is, like how big would it be a cell, or how small would it be a debris. So the purpose, so the role of the computer here is to build this tree, is to train this tree, is to find the threshold value. So you can have a clear flow chart of if the segment area is bigger than A, then it is possibly a cell or debris. And then you look at a second feature, if the elongation is bigger than B or not. And then in the end, you will have some classifications. With these classifications, the machine will find out the best model to do the future prediction. All right. This is the first method. And the second method is a little bit more complicated. It's called the artificial neural network. Unlike a decision tree where each point is a yes/no question, the artificial neural network is trying to weight all the input, all the features. So for example, if I use the same example of segment area, elongation, they will be inputted at the same time, and they will be given some weights. And based on these weights, it would be considered an input into a function, and there is an output. And with this output, you can use this output to compare with the real output to see the differences, meaning the error. And then you feed it back to the training process to minimize the error. So that the machine can decide what is the best weights to yield the most accurate output, or what is the best function to yield the best output. There are some features, and you give them some weighted sums, and then you send them into a function, and then you have an output. You compare this one. And then you try to minimize the differences between this one. This is the supposed output and the real output. And you do this iteratively or in different layers. Then you can find the best combination of this function and the weights on the features to find the best trained model. Yeah. So after I talk about these two, I want to talk about also the pros and cons of the two. First, I want to talk about the cons of artificial neural network. Most of the time, the process could be a black box. which means that you don't actually know how many nodes you need, or you don't know the details of the algorithms. And that would be a con because it could take too much time, or it doesn't need that much layer for the same result, for the same result to happen. And the second, so these are the two cons of two disadvantage of artificial neural network. And then, whereas the decision trees, it could be very complicated. Imagine that you have 100 features. So in this tree, there would be 100 branches at least to separate everything. And then the bad thing about this is that it will be very complex because a decision tree is you're only examining one thing at the same time. So it is like if you have a value, it's only segmenting the space into two, yes or no, and then the second part, yes or no. So you're constantly putting rectangular boxes into this space to categorize different things. And so imagine if the data itself is not distributed very nicely, then it would be very complicated for the decision tree to run. So maybe in this case, it's better to run the artificial neural network where you consider all the features at the same time, and then you give them, and then the machine gives you the best weights and the best function for the prediction. These are the pros and cons. And so I'm going to talk about one example of decision tree where from this paper, which is cited as a reference in the review paper. They are trying to see the hematopoietic hematopoietic stem cells in the 3D environment. And because it is, so I'm going to talk about who they are. They are stem cells that have the potential to develop into multiple lymphocytes and blood cells. So they are called hematopoietic stem cells, and they live in the bone marrows. So, HSC has the potential to develop into different cells, but it needs a good environment. And the researchers in this research, they care about what the environment is like. They want to visualize this environment. In the bone marrow, there is endosteal niche and then perivascular niche, yeah. And then this is a cartoon image. But what if we want to see a real image of of how these innocent, untrained hematopoietic stem cells get induced by the signals, and how do they move to different places? So we need to visualize it in the bone marrow. And there are two challenges. The first is that the bone marrow structure is very complex. It is not like this room, very rectangular. It has many substructures. And the second part is that when you visualize an image from fluorescence, when you go deeper into the space, the signal will be losing more and more, and there will be scattering because of optical phenomena. So for a human eye, sometimes it is very complicated to know if it is a real cell or if it is just some signals from other places, or if it's a cell that has a malfunction. So that's where the software kick in. They develop a software to distinguish who are HSC cells and who are not. And this is called the training of classifier. So in the 3D space, they train the machine to classify, they classify these cells into three categories. First is HSCs with a smooth surface, and the second is surface but a little bit rough, not totally smooth. And the third one is with very irregular shape, which are considered to be false HSC, so false signals. So this is manually prepared. This training set is manually prepared, and this preparation is based on the morphology of the HSC cells. So after they trained the machine to know these criteria, this decision tree, they can have the result of who these three are. And you can see that this green one is a class 1, which is a smooth one, and this one is an irregular one, and this one is a class 2. And this is what the computer is telling you. So this is one application of decision tree in 3D images for the case of HSC cells. All right. And the next method I would like to talk about is the active learning. It is a semi-supervised learning in the sense that you're not only the user is not only putting input once. Because even though the machine can train to have a decision tree, sometimes there are some confusing examples where the machine doesn't know where to put the categories to. So in active learning, the human at this time, the machine would ask a human, how would you like to put this irregular shape or I don't know what into this class or into this class. So you are iteratively adding feedback to the training model. In this way, in active learning, it is semi-supervised because there are more human input, and it could be potentially more effective based on the paper. So in here, not all the data are labeled. First, you have labeled data, and then after the learning model, you have an unlabeled data set. And with this, the machine, if it is confused, it would ask the human, how would you like to label, or do you want some new labels on this data? And then you put this information into another training process with many times, and then you have a better result. That is what I understood active learning. And one application is which is mentioned in the paper, is when you want to track the cell. Imagine if you have 2 frames from time I and to time I plus 1. How do you tell how do the computer knows that it is this cell to move to this cell in the next frame, but not this cell to this cell? The computer doesn't have the consciousness of knowing that, oh, maybe this cell, if it doesn't move a lot, it doesn't go to this cell. So in this case, how they model this is that they propose 4 links because there are 2 objects here and 2 objects here. And then when the computer is confused, he asks the user, is this link true or not true? If this link true or not true? And if this is true, not true, or if this is true or not true. So in this case, if a user could tell the computer that this is true and this is true. And this could be an experience for the computer to run further frames. And so in this case, it is a process of active learning. And for the last part, I am going to talk about unsupervised learning. As I mentioned before, the purpose of this learning is to explore the data structure. So the first method used is dimensional reduction. Oftentimes we have many features on one data. For example, for an image, you can have area, you can have parameters, you can have the fluorescence intensity, and you can have the color. It could be many, many features, but sometimes they are highly correlated, or sometimes they are totally independent. So I want to know, so dimensional reduction is a method to reduce high-dimensional data to 3D or 2D, where researchers can visualize. And one method that can be used is called principal component analysis. So as a simple case, if you want to transform a 3D graph into a 2D graph, how would you do it? The instinct is that you have to throw away one dimension. Then this analysis is an analysis that throws away the least useful information, the least useful dimension. So if you look at this cluster, this gathering of data, if you put a plane over here, and then you define a new axis called first principal component and second principal component, And supposedly there should be a third one, but this third one has the least influence. So if you throw this one away, you can keep the most information, or you lose most little information when you transform this data into a 2D. And after you successfully transform the data into 2D, or from six dimension to 3 dimension, there might be chances that you can observe some clusters, which means that these. So here is another example from the paper, and I think that with the cluster, it can only tells you that there are some differences between this part and this part and this part, and then it might be related to the features. But it is a reduced image, so the axes are already a combination of all the features. So you have to do further supervised analysis to know what the features are useful. But how it is useful in unsupervised learning is that it can tell you if the data has clusters or not, which can be useful in classification. Yeah. So lastly, I would like to talk about like a summary of the takeaway. So of course, machine learning has a strong potential in the field of image learning, and secondly, in supervised learning, it proposes a model that can be used for prediction based on manually labeled data. So here I want to talk about if everything is biased or unbiased. In the last part of the paper, it discusses, it states a point that machine learning is not totally unbiased because you are manually labeling data already. So you need, for me, it is like a cooperation between human and computer. And the role of the computer is only to do calculations and repeating. But there are inputs of human expertise. For example, a computer wouldn't know that these are the important features to start. A human has to tell him. But the human doesn't know what number this is, and the computer can help him find out what these numbers are. The common goal is to minimize the distance between the proposed output and the real output. So here, I would say that it is not totally unbiased because you have to trust an expert. And if you ask a dummy to define these features, maybe you have a very bad result. This will be all for my presentation, and you can ask me any questions that you have in mind. Thank you very much for listening.
I know that you have some questions. So we start.
Yeah, it's really simple. In the first diagram.
The first diagram. Which one? This one, great.
What's the difference between algorithm, or in this case, in a model?
You mean
In the concept of the step 3A and the step 5.
3B? Oh, step 3A and 3 and 5. Yes.
Yeah, in the concept or in the application or the math. I don't know.
Okay. I would try to say that you have the algorithm part can be considered as, for example, of neural network, these nodes, the weights you give them, and then after there is a combination of weights and input, you put it into a function to have an output. This is the algorithm. This is one part of the algorithm.
But the step in the hidden layers, the algorithm is a fixed part, or is the part of the modified?
The
I mean, if you want to go into further detail, for example, the example that Andy gave on the neural networks, one algorithm to train the neural networks is the most famous one, called the backpropagation, who evaluates the weights of the networks until the end. Then it checks if your output of the network is equal to the expected output that you have some targets, some classification that you want to do, etc. then brings that error and updates from the last layer to the first one in one pass, one time. How can I say?
Let me.
The update is from the last one to the first one. That's one way to train the event, but usually you can use one algorithm. You can use another method to update the same weights using some other scheme, like a random test, varying in a random manner the weights of the net, checking if the result is better. If not, you then propose a new random order of the weights and you try again. So the algorithm here is based on how you update the parameters of a model, and the model is the mathematical equation.
And also your question about the difference between algorithm and model. This is why you need evaluation, because okay, there is a imagine the first time you put, and then it gives a weight of W1 to Wn, and then it plugs this into a function, and then it has an output. You don't know if this output is a good output or not, so that's why you need an evaluation to compare the output with the output of testing dataset, and there is a difference. With this difference and the evaluation, you put it back to the algorithm. So the algorithm knows that, oh, previously this is a bad combination of weights, or maybe a bad function, and then it would remodify. It would give a new random set of W of weights to put, and if you run this for many times, you would have a maximum accuracy and a set of good combination of weights. And this is the model you can use for future prediction. So I would say that the model is the best fitted model runs by this algorithm. That's the difference, I think. Yeah. There are more questions. Any questions? Doesn't have to be related to this, to my life too. It's okay.
About the sampling, how do you know what is the number of samples to do the training dataset?
Oh, you mean how do you know what number I split into these two?
Yeah.
I read somewhere that it's best that this is 75% and this is 25%. But how do I know if it's we don't really talk about it, but I mean, in my first imagination, I think there should be 50-50, because you need to match every output to one output here. But you don't need to use all the resources. So maybe if you have a bigger set of training set, like 75%, you have more chances to produce different kind of models, and you compare it to only 25% of the testing, then the accuracy would be the biggest. Yeah, I think this should be more than this, and there should be a curve of accuracy and a percentage of this, and then I think it will reach biggest point at 75.
How do you split the data into training and testing data? I think it's a little bit relative, because at the first thing you can think that even with more data your model will be more robust, because but that's not a good thinking, because you can overfeed the model. When you're overfeeding the model, your model is only representative with your data set, and the goal that you are going to achieve is that your model is generalized. And I think that you have to look at this case by case, and to say how you can split the data into training and testing data set.
You said case by case, but in a specific case, what do you see in the data set when you thinking, oh, it's better?
You can make a loop with the tweaking of hyperparameter. You can think a model with 50-50, 25-75, and 30-70. and then you see who has the best accuracy. Here is who you.
In some sense, the main concept or the core concept behind the split of the training and test data is to have some algorithms or mathematical model that you want to fit. And if given that you have some number of samples, let's say it's the training, you are biased to the samples that you choose. So one way to know how many or how less is to check, well, how can I measure the bias given my sample data? So if you take a lot of data to train your model, maybe your model knows a lot, but you are left with very few data to say, well, can my model generalize after I see new samples? So that's a trade-off between the variance of the results of one model to have more data, or the bias of the number of sample points that I have to choose. So it's up to the researcher of the application. There are some techniques that usually help you do that. If you want to check overall your samples, you can switch between train and test and train performance.
Yeah.
Yeah. When you're talking about the different kind of machine learning, for example, the supervised method.
Where? Supervised? Yeah, here.
This one, or
Oh, okay.
no problem. For example, if you have in this family of the supervised, I think exists different kind of model in the supervised family. Then, how do you know what is the best? Because if you say, oh, this is not good enough, I have more data set to train it more, or what is the best method? Is need less sample, or do you have a specific readout in the algorithm or in the model?
I think I have the same doubt as well, that here, for example, decision trees. If you run the first test, you have a train model. But if you run the second test with a new split of 75-25 for training data and then testing data, you will have a second best fit model. So in these two models, how do you decide which one is the best? Is that your question? Okay, and so we talk about that. So besides decision tree, there is something called random forest, where you have different good models in the end, and then you kind of choose the average result of this good model.
Yeah.
That's that's what I get from what we discussed. So you don't just train it once, but you train it many times, and then you will have a forest, like a first tree, and then the second tree, but you don't know which one is more important, because here, how do you know you have to put segment area first, but not elongation? If you do a second trial, maybe the computer will tell you that elongation first and segment area, and then you have maybe the similar accuracy. You want to add? Yeah.
Okay, in supervised learning, you have to choose the model based on the type of task you want to do. For example, if you want to do a regression or a classification, there are some algorithms that best suits that type of task. I think super vector machines is best for classification. Random forest, I don't know. And here, and with that information, what task you want to do, you are going to select the type of algorithm that you are going to use with your data. Because the algorithm is, based on your last question, what's the difference between algorithm and model? I think that, with my understanding, the difference is that the model is the algorithm already trained. So the algorithm, you have a standardized method to learn, with a standardized method of error function, and the model is that algorithm already trained with your data, and that you have your model. So this is that.
And I think a little bit of information also, if you want to understand example, a neural network, is because we try to mimic in some fashion, in some way, with an algorithm, with a mathematical model, to mimic how learning the process is made. So artificial neural network uses the model actually from the same brain to try to mimic the inductive learning. You have a couple of examples, and you perform a general rule, and that will be applied to new examples. And you know if you want to learn when you're little how's a chair, and then you saw later in the future a chair, you also know that that's a chair, even though you saw a very few examples when you were little. So the thing is with this machine learning, when we try to put some math or some mathematical foundation to this core concept like unsupervised learning, active learning. Also, it depends on what is your personal flavor.
Yeah.
But yeah, there's no other core model that solves all the problems. Actually, it's a problem that is reviewed in terms of machine learning and also a little bit neuroscience. Because they say, oh, we wanted to have a real deep learning neural network that can solve anything. But that point we haven't reached that.
Is there a marker? Like, I can have an example of doing both decision tree and neural network, and maybe one is more easier than the other for Jorge to know. So if you have here and here, there are some. What artificial network is doing is to find, even in classification, is to find maybe a line, a function that can separate two data. And what decision tree is doing is to do this, the first step, and then you need to know a second step. So, so we have two features, and then we need two lines to separate the space to know how they are different. And in this case, this will be easier, take less time, because they are very distributed. But for the neural network, maybe it would take many layers to find out this function. And they would be not unique, because this is a useful one as well. If you split the data into other, this would be a useful one as well. But if this graph is very complicated, then you need many times of this, then decision tree would become very inefficient. And maybe a neural network would be faster to learn. For example, if you have this kind of distribution, and then this kind of distribution. Maybe a neural network can directly tell you that there's a spherical function that can separate the two. But for decision tree, you need like 1 time, 2 times, 3 times, 4 times, or maybe try and error to adjust this value. And in this case, I think machine learning, decision tree would take so much time and complicated. So you have to look at how your data is like in the first place. And yeah.
With the same example, I can tell you that for every example, if you have the example that above, where the two labels are really separated, I can say that support vector machine is the best machine learning model to do that task, because support vector machines searches for the best line that separates the data. Yeah. And you have to know what the algorithm is doing to give you the final result, and then you can choose what algorithm is best suits your data. I'm answering your last question.
Good question, yeah. Good question.
The last question with no questions. So you guys ask first.
Oh yeah.
How do you make the decision if I have to choose a machine learning method or I think a generalized linear model, or imagine How do I make the decision for a random forest model or simply a linear regression? Or for example, a classification task, how I decide between a supervised machine or a logistic regression method? What is the...
Oh, like what consideration should there be to know, do we need machine learning or do we just simply need a regression model? Wait. Do you mean the regression as in super, or just a linear regression model? I think it depends on how complicated things are. Like, of course you can use a machine learning to learn a very already linear distribution. And then in this case I would say that there is no need for machine learning because it is clear to the human eye that I just need Excel to find me a best fitted curve. When we need machine learning is that we don't know what the model is like and we don't know how to guess. So we let the computer to guess. But what we know is that we want the minimum error between the guess model, the output of the guess model, and the real output. But for the human eye, maybe it's very, very difficult to propose a method. For example, if you observe 36, 6, 49, 7, 110, mathematicians define functions of square root. And actually the machine is doing similar stuff. Because if you have a model that says that 100 output 14, 14 and 10 has 4. So the goal is to make this 4 disappear. And this is what the machine is doing. So when you want to do machine learning, it is when data are more complicated or there are more than one features if it's a high dimensional space. If there's only 2 dimension and you only want to classify like this, I mean, I can just do it in 1 second. So yeah.
Maybe I would just like to add that also you can make them complete. You know, like you can.
Oh yeah.
What is the prediction of the linear regression, the random forest, and if
Mm.
then something like a decision tree could be a good thing because it takes like in a 2D space. It takes like this is the decision, then I take another decision. So it's really good for like this kind of thing. So then maybe when you get when you are experienced with that thing and you see the plot, and if it's very curvy, maybe then like a support vector machine with a kernel that is like spherical will work well. So
Mm.
you can take from the knowledge like to take a decision, but also you can just run the things and choose.
Yeah, to find out. Yeah. Is it do you ask because you don't know or you have some thoughts too?
It's a thing that I have been thinking a lot of time.
Oh, okay.
It's a personal...
Oh, great.
After this because maybe I got a little bit more technical, but I wanted to ask you something about
Yeah.
your review and the
Oh,
things
great.
that you learned about machine learning this week. Maybe
Okay.
a couple of weeks.
Okay.
Because do you know, well, do you feel that you know now something different that you know when people talk like you show us two examples of unsupervised learning, supervised learning, active learning, semi-supervised learning, and so on. Do you have now a grasp to maybe differentiate to know, oh yeah, I have some data, maybe in a clinical application. I have to, in the future, maybe take a decision even a patient arrives that has some symptoms.
Mm-hmm.
Maybe I have my anamnesis analysis and I say, oh yeah, this is the primary diagnosis. But then some other person say, oh, I have this machine learning algorithm that does this or that. Do you think that you are more prepared to understand how can we use these methods to analyze, say, like a clinical one, for example? Do you think that they could be applied? Do you think that no?
I think I'm more prepared, not in the sense that if you give me a data, I don't understand the algorithm because I don't know the math behind it, and I don't know if really people who know the computer science who design programs know the algorithm or have to know or is important for them to know. But as if I work as a doctor, I need to know what's important for me to know is how the machine learn and how the machine evaluate, and at least what kind of learning that is, for me to not to trust this machine, because for example, if today this decision tree, it's like if this person has cancer or not, to answer this question, cancer patient or not cancer patient, and there are different kind of threshold values, and I can know, and after this week I can know that if you have different sample trials, you can have a different kind of tree. So how do you know if you use this method, how do you know this A and B can be really trusted? Maybe it can be only trusted because the input for this input, for this set of data, but you cannot apply this for a bigger set because it would overfit, as you said, or underfit. So that is the ethical impact, probable ethical impact for physicians to know what this is, and to know that this is not almighty God of predicting everything, because it can only tell you a possibility of a certain case. This is my opinion. Yeah.
And did you have a different opinion before knowing all of these things?
Before before I'm already doubtful. That's why I want to know. But in theory, I think yes, math is very powerful that you can predict. But now in real life, I think this is very helpful. But you need an expert who oversees this process, who knows what things he's labeling. When I was doing the Weka nucleus, I could easily make mistake too, to give the computer to tell him that this is a border, but I can give him a fluorescence and a dark at the same time. But I'm very scared that how does the computer really know? Yeah. So there could be some false positive results too. Yeah.
So you rather believe in a tree or in a neural network for a clinical application if you had to choose?
Oh.
Which would suit you best for you in terms of the interpretability, maybe?
Depends on what kind of things you want to predict. If you want to predict if this patient would have, for example, if diabetics, you look at the concentration of blood sugar, or how many times you eat McDonald's a day, or how many times you drink wine a day, and to see if a patient to have diabetes or not, then you use decision tree, because this question is yes and no. But if you want to know that a certain number, for example, the likelihood of this patient to have or this population to have diabetes, then you have a population 1, 2, and 3, and there's the real likelihood, and then if the result is a number, the prediction result is a number, then maybe artificial neural network is better. If you have many features, like how many times you eat McDonald's, how many times you eat alcohol, how much blood sugar you have, and then you give them the weight, and then you find a model. But then it might be a very meaningful model. It could only happen in the case, like it could only happen coincidentally to give you a good model in this case.
It's
Yeah.
You know what it's doing, not necessarily.
Yeah, but not necessarily. These features not necessarily have a correlation, or they could be highly correlated. For example, if you eat 5 times hamburgers, you will have high blood sugar. There is already a correlation. So why do you need to put it into 2 modes and apply and put 2 weights onto it? But I'm not sure if the machine learning can tell you that this is unnecessary or this is necessary. Yeah.
Well, I think in the mode is like pretty obscure. But yeah.
Yeah, that's my thoughts.
So I think we are ready. Let's give Andy another applause for
Okay. Thanks everybody as well.